about before in the earlier session. So we're talking about campus networks now. So I've tried to outline a couple of rules that if you follow, your campus networks will work pretty well. And I have zillions of pictures. So the first rule of thumb is, and it only makes sense if you think about it, minimize the number of devices in any one path. If you've built a network to where somebody depends on 50 things working for them to have service, they're going to have less reliable service than if they depend on 5 things working. I mean, it's really quite simple. I want you to use standard solutions for every one of your common situations. So a network inside of a building should look the same inside of every one of your campus buildings. I don't want, you know, the network inside of your administration building to look any different than the network inside of your faculty of social sciences. Every network on your campus ought to look the same. Maybe it has a different number of switches, maybe, you know, they're different models, but every network ought to be the same. And I can't re-emphasize this enough. I would like you know, I could drop, in fact, at the end of this talk, you guys could come to my campus and you would know, you could walk into any building on my campus, you would know exactly what the network looked like in every building on my campus. Because I have this cookie cutter solution, every building looks the same, all right? So I want you to do that. I want you to build separate core networks and separate edge networks. We'll talk a lot about that. I want you to provide your services, your email, your web, whatever kind of services you're provisioning on your campus need to be provisioned near the core. I don't want your bursar's office to have their servers in their building because they have to put their hands on it. I want those to be in the core. I want to separate your border router. So your campus ought to be segregated so that you have some core routers and you have a border router at the edge. Well, we'll talk a lot about that, and that's going to be very, very important, particularly if you end up picking the model that your NRAN is a peering network and your campus has to run BGP. You must have a separate border router at that point. And you ought to structure your network so that you have opportunities to firewall and to shade network traffic and to put security devices in your network. So let's talk for a minute about the core versus the edge. The core is the center of your network. This is a place where you can focus your energy on reliable power. So you can have generators, you can have batteries, and reliable air conditioning. You might have on your campus, depending on what your campus structure looks like, you might have multiple core locations, and you always route in the core. The core is a routed network, right? The edge is towards the edge of your network. This is what I talk about when I talk about the edge of a network. It's every building on your campus. It's not your core. Okay? And you always switch at the edge. So let's look at just the simple minimize the number of network devices in a path. Build star networks like the top, not daisy chain networks like the bottom. Often it's easier to build daisy chain networks, but they're less reliable. If you're a user, whoop, sorry about that. So if you're a user here, you depend on this and this and this and that working for this network to work. If you're the same user here, you're only depending on your switch and the aggregation switch to work. So just a very simple technique. This is what every network inside of every one of your buildings ought to look like. Make it look like that. You ought to have a switch that connects to the outside the building, and it provides service to every switch inside the building. Don't do this. So these edge networks, they're just layer 2 local area networks. They provide service to the end users. Each of these is going to be a separate IP subnet. Separate subnet from the building next door. I would plan for no more than 250 computers on one of these. But you can make them a little bit bigger. Don't make them 2,000. And you should have one subnet or one edge network for every reasonable sized building. And I have a lot of examples of these. Again, the network should be switched. And the thing in red here, so important. Always buy switches that are managed. If you have unmanaged switches, most of the stuff we're going to teach tomorrow, everything we're going to teach tomorrow, you can't do. And you can't understand what's happening in your network if you have unmanaged switches. Yes, it's cheaper. Yes, it works. But you can't tell what's going on. It's like driving a car without a gas gauge. How do you know when you're not running out of gas? Without an oil gauge, how do you know when your oil pump's when your engine's going to seize up? You don't know. You have no idea. So you have to have managed switches for you to be able to operate an effective network. So back to these edge networks. Every one of the networks on my campus looks exactly like this. This is a building. Somewhere in the building, I bring fiber in from my core location. It terminates in a fiber SFP on this switch here. I call that an aggregation switch, or sometimes we'll call that a backbone switch. It connects every other switch in the building. Okay? Now, when you're growing your network, you can't really afford to do this. You can't really afford to buy all these switches. But, you know, you don't need everybody to connect everybody in the building, so you can start incrementally. You can put in the aggregation switch in the fiber and connect up the few computers. And then when somebody kind of at the other end of the building needs to be connected up, all right, well, what we can do is we can run some cabling out to a new network rack location like this, connect up some computers there. All right? And then we can build a little bit more incremental. Somebody at the other end of the building needs to have some service. So we run some cabling out to this location, another network rack, run cabling out to those computers. Go. So you can build incremental until you can find a picture. Right? So again, this is the thought of having a plan. The plan in your network, any building you're going to serve, you're going to make fiber to it. You're going to put an aggregation switch there. People that get served, if you can't cable to that switch, then you're going to put another network rack in some other location in the building. You're going to put some cable between that network rack and your aggregation switch, and then you're going to cable from that edge switch down to the individual computer. That's your plan. That's what you're going to do every time somebody wants to put network into the building. Period. Right? And if you do this, everybody knows what your network is like. If you have a turnover in your network technician, so one of your network guys leaves who really understood everything that's happening in this building, doesn't really matter that much, because guess what? You know exactly what the network looks like. Everybody knows what the network looks like. You just need to know where these locations are. And if the switches are managed, you're going to put an IP address on them. You're going to put that IP address in the DNS and give the thing a name. And guess what? Then just the name of the switch tells you probably exactly where it is. It's going to be the name of the building, dash, room number, or dash, each computer lab, or whatever, the name of the switch is, right? So you can help yourself a lot from a documentation perspective and from a perspective of having your network be simple and understandable by following this kind of rule.
switch over there. Don't do that. There are times when you got to kind of sacrifice your morals, and you got to say, okay, I'll do something. But if you're going to connect these up, at least connect this switch to the aggregation switch, right? At least connect this switch to the aggregation switch, so that you're trying to collapse the diameter of your network. You know, if you do it the way that was originally drawn here, this guy here depends on that switch, and that switch, and that switch, and that switch stop over. And you can make it simpler by connecting them. Okay? What I like to do when I'm planning my network is where you have a couple of small buildings close together that aren't going to see a lot of use, like here. Like on my campus, there's a section on my campus that used to be a residential neighborhood. It used to be where houses were. And the university just turned the houses into offices. So there were faculty offices that are very small. Like there'd be 5 faculty in one building. And then the next building next door, which is very close, 10 meters away, is 5 faculty. And the next building is 5 faculty. Well, I'm not going to put fiber in every one of those little tiny buildings. What I'm going to do is I'm going to run fiber to one of them. I'm going to pick one of them and run fiber to it. And that's going to be where I put my aggregation switch. And then I'm going to run Cat 5 or fiber, whatever it takes to reach the adjacent little house. But again, this network looks the same as the other one. It's a star network. There's an aggregation switch here, and then these switches here, right? I'm not daisy chaining, but I'll go back to the aggregation switch. Another thing that's possible, although I'm not quite sure why you would do this, is if you had fiber to small buildings, you could put a switch in the core location and run fiber out to individual locations. But if you have fiber, probably you could just route those even though they're really small. All right, let's talk a little bit about the core. In the core, I want you to route, and we'll get a bunch of pictures that really emphasize this. But routers provide significantly more isolation between devices. In particular, they stop broadcast. Now, I remember I gave the example of, somebody in some lab sees an empty cable and they go, oh, I wonder why this isn't plugged in, and they plug it into the switch and they create a loop in your network. Now the question is, why does it kill your network? Do you know? It's broadcast. Because what happens is when a broadcast hits that switch, the switch sends it out all ports, including the port that's looped. So that broadcast goes out the port that's looped and back into the port. Oh, now we receive another broadcast. It sends it again. Oh, receive it again. It sends it again. Every broadcast on the network won't die. It stays alive forever on the layer 2 network. So when somebody does one ARC or some NetBIOS request on a Windows machine, that packet starts to live forever on your network. And then the next broadcast, it lives forever. And pretty soon all the bandwidth of your network is gone. Totally taken up by broadcast. So loops in your network are killed. What happens is you kill yourself with broadcast. Routers stop those. So I've seen campuses that have one big giant layer 2 network, all one subnet. Now they might have allocated separate IP addresses for the buildings, separate IP address blocks, but the center of the network, it's just a switch. So somebody in some lab like this goes, oh, let me plug that in. The whole network across the entire campus stops. And so you're the network administrator. You can't even get your machine to look at the network management station because your network is closed too. All of a sudden you have to start going around and unplugging. Fine. It's a terrible position to be. Routers stop it. So this is really, really a key function that you need to understand. Routers stop broadcasting, and that's a really big thing. So routing's a little bit more complicated. There's switches, you can just blindly plug them together and they magically work. But of these links here in the buildings, and the links between the routers need to be routed. And a good illustration of why you want to do that at this level is as follows. If this is a switch network here, if all of those links are switched, if all those links are switched, you have a loop in your network. And we already talked about loops in your network means broadcast loop. So what do? You turn on span tree, right? Span tree prevents loops. How does it prevent loops? The way spanning tree prevents loops is it detects a loop and says, oh, we have a loop, and it disables one of the links. It says, all right, we're not going to use this. We're going to disable this link here. These interfaces will be disabled, and thus we have no loop in it. Right. That means we are using non-optimal routing. If somebody here wants to talk to somebody here, guess what? Those packets are going to go this way. Right? It's non-optimal. If you switch, if you route, the routers are smart enough that they know, number one, this is one subnet, this is a different subnet. This router knows that the best path to that subnet is this direction. Bingo. So you know. Right? So in the core network, there's a lot of bullets, and you might want to look at these later, but reliability is the key. Your core, multiple buildings, many people rely on. So this is where you want to put all your energy and emphasis on generators, on batteries, on air conditioning. A place like this, where we have a network rack here, a couple of switches, do I really care? Am I going to put batteries on this? Probably not. The lights go out here. Well, I suppose if we have UPSs and all machines, yeah, maybe. But generally, on my campus, I don't provide UPSs or generator power on the switches in individual buildings. Because if the power goes out building, their computers are out, why do I care if the network's out? It doesn't matter. On the other hand, in the core provides service to all my buildings. If it goes out, everybody's out. That's where you want to put all your investment, generation, and batteries, and air conditioning. Then you might have one or more core locations, and I actually have some examples of exactly what my network looks like. So power, reliable air conditioning. As your network evolves, one of the things we have found that if in your core you have a UPS and all your equipment's plugged into UPS, what happens when the UPS fails? Same thing, right? Basically you're out of business. As your network evolves, one of the things we probably want to start to think about is buying devices. Of course, we don't really have any examples of core network hardware. But you can buy core network hardware, core switches, and core routers that have two power supplies. That's like dual power supplies. If you have two UPSs, dual UPSs in your core, then you can plug one power supply into one UPS, one power supply into the other UPS, and guess what? Now if you have a UPS failure, big deal, it's still okay. So redundancy and reliability are key in the core. In my cores, I have dual UPSs, two big UPSs. I have two power feeds from two different directions to my buildings. I have redundant air handlers, so one air conditioning unit fails, no big deal. There's another one there that can take up for them. So everything I do in my core is redundant, as much as possible. And I'll show you a picture and I'll show you where I'm not redundant, and I'd like to fix it. I probably will sometime. But the key here is the core is where you focus your redundancy and reliability, not in a building again. Okay? All right, and then you want to have at your core border routers. You need to separate those from your core devices, and I have a lot of examples of that, so we don't have to go into that. This is where you can have firewalls, traffic shaping devices, various security measures, intrusion detection, intrusion prevention, and where you do NAT. different than this goes. You know, here you might be doing things like, notice I have no NAT box in here, so these machines are open to the internet at large. So in this case, the border router, I might configure that to filter certain things. It might route certain kinds of traffic that's really dangerous. For example, I would never, ever, ever connect Microsoft Active Directory server to the internet and leave all the Microsoft ports open so that they can be attacked. It's a common attack vector for Microsoft servers. I probably would be very hesitant on a Linux platform to open NSF, the NFS, the network file system ports to the outside world. I probably want to be filtering those simply because it's a really, really common attack. So this guy on the border, he might need to make decisions about which direction to send traffic, and he could be routing certain types of traffic. Here, we want to be passing all the traffic. So, you know, they're different functions. They really think about different things. One connects to the outside, one connects to the inside. All right? So, if you're going to NAT or firewall, this is a common place to do it. Like, this is probably what a lot of your networks look like. You might have some kind of border router. This might actually be provided by the ISP. Then you have some kind of NAT box, and then you have, some of you will have a core router, some of you have a core switch here, and other things in the building. I've seen it with your networks, so I know. An alternative, one of the things we're running into in the United States as our speeds have gone up here are unhappy. Because they can get large flows this way, as soon as they hit this, they're finding they can't really go as fast as they'd like to. And just for reference, the RINs in the U.S., virtually all RINs are connected to the network backbone, to the Internet tube, and MLR at 10 gigabits. 10 gigabits, okay? Many of them provide campus network connections at 10 gigabits. So the reality is, these guys, if they're connected properly, could push multiple gigabits up through this firewall NAT device. I don't know of a NAT device that can run 10 gigabits. I don't think such a thing exists. So this architecture can be a problem for scientists. And we in the U.S. have as we've really started to push upwards into provide central services for the entire campus, you really ought to put them in your core location where you have the power, the air conditioning, where you can control the switch, where this is probably just a short copper cable from this router to that switch, and those servers are all probably going to be in the same room as your stuff. Okay. So let's talk a minute about the border router. This is the most extreme case of a border router, and we might actually see this in some universities in Lagos where there is an internet exchange, where they actually connect to the REN, have their own connection to an ISP, and have their own connection to the internet. And again, the border router needs to make decisions that are different than the core router. The border router has to decide how to move traffic off your campus. The core router is simply moving traffic inside of your campus. And again, REN's appearing. We're talking a lot about providing independent network space, autonomous system numbers. I won't go into that. So try to put this picture all together. So we talked about what does a typical in-building network look like. So these are in the building. Right? And then this is your core location. Probably some other building somewhere. Right? And then these are fiber optic. So that is the best practices of how to build it. These all must be, each building connected here must be a separate IP address space, separate subnet, and this thing needs to be acting as a layer 3 router. It's routing, not switching. Now I've seen cases where some folks have a switch here and they actually put a little router down here so that each building is its own separate IP address space. And that's fine. I mean, that's a reasonable strategy to give yourself the isolation. The problem you're going to run into as you grow is the cost of these routers for something to 4 gigabit Ethernet speeds is going to be picked up on one here and here and one there and one there and one there is more than buying one up here. But the campus network architecture is right. It is correct. Every building has its own separate IP address space, its own broadcast domain, and notice it's a very simple incremental strategy to swap out this core switch rather than this thing being a switch and the router being down here. All I have to do is put router up there, remove the router here, bingo, you're done. So it's a very nice incremental strategy. So here's an alternative core design, and I actually have seen this too. This we call a one-armed router. What we do is on this, this is a switch now, not a router, and we use VLANs. And we allocate a VLAN, maybe this is VLAN 1, to this network, VLAN 2 to this, 3 to that, 4 to this, 5 to this, and 6 to that. Alright? Your router sits off here, it's just connected to the core switch. And you use VLANs. These are trunked VLANs. Trunked and tagged. And essentially on this link, we use VLAN tags so that the traffic on VLAN 1 will come up here and hit the router. So it comes up, hits the router. The router sees that it's for VLAN 2, it changes the VLAN tag to tag 2, and it goes back down. So this is called a one-armed router. Again, not a bad strategy, because if you couldn't afford to buy that core router, this is a reasonable way of doing it. You could do a nice one-armed router with the equipment that's right here in this lab. So today, if your network is one big flat network, you can take one of these switches, I'd probably take the one on the bottom of the stack, or one of these routers right here, and one of these switches, and you can make yourself a beautiful campus network doing this. And would actually perform quite well. The switch at the bottom of the stack has gigabit Ethernet ports. You can do a gigabit Ethernet backbone. Not bad. Now you're going to be, ultimately at the end of the day, you're going to be limited because this is going to be the bottleneck. That link back and forth between your core router and that core switch is going to be the bottleneck. It's going to be limited to 1 gigabit. If these are all gigabit links, we can deliver 6 gigabits, but that guy can only do 1, right? So, again, it's not a bad strategy for building the right network architecture. Again, I see that if I have the vision that what I want is a subnet per building, and I go to my director who goes to the vice chancellor and says, we need to buy a core router with a bunch of optical interfaces, and it's going to cost $40,000. And the vice chancellor says, geez, I don't have that kind of money. Can you do it cheaper? The answer is, yeah, we can. It's an interim solution, and it won't last as long for us, but yes, we can. We can take some donated equipment. We need to make sure that we did have the fiber optic links. We would need to have some fiber interfaces, and we need a core switch and a router here. But again, there's route. Those switches that are sitting there are fine for a core switch, and there's a router there that's fine for a core router. You have a gigabit Ethernet backbone. Does anybody have a gigabit Ethernet backbone today? So it's better than maybe anything that we have today. So, but it's not that bad of a strategy. That's not exactly what we want. What we really want is that this to be a core router. We want this to be a router and not to do this core router. But again, it'll work. And it gets you towards, I'm walking towards my end goal. So it's not a bad strategy. Some of you can afford to put wireless into every building, or can afford to put fiber into every building, and you need to use wireless. Alright, fine. We can do that. That's a fine thing to do. Do it intelligently, alright? So first off, remember, every subnet uses broadcast. Broadcast take up band. So I would never put a wireless antenna here to serve these buildings, even though it might be close. Always, the wireless antenna is directly off a separate routed interface of the router. Now, we would be best off if we use very directional antennas and only serve one building per antenna, or per radio link and per interface. We'd be best off if I had a separate interface for every downstream building I was serving. But maybe I can afford that. So maybe I put some kind of omni antenna here, and I pick up a couple of the small buildings at the edge of campus. Put an antenna on the top of them, pointing the omni, and you pick up those buildings. Fine. You still keep the same picture. You still have the same vision that when you can afford to put fiber, you're going to do it. So, again, it's building this vision where you want to go, but you can't always quite get there. You can't always get there in the most direct path. You know which direction you want to go, and you go a little bit around go around those trees. Maybe they're too hard to go through. So just need to keep in mind where you want to go, and keep this architecture in mind. The routing the core, the switching the other. Here's a more complex core design. This is where we have 2 core routers. The core router here, the core router there. Maybe it's a large campus like this. I don't really want to run fiber from this building to every other building. It's a long way. So maybe I want to have a core on this side of campus, a core on the other side of campus. So everything on that side of campus is fiber to that core. Everything on this side of campus is fiber to this. It's fine. So again, this is your core location, and each of your individual buildings, these are all fiber. That makes sense? Right. Here's my campus. This is my campus currently. I have 2 cores. One core is outlined in this green, and the other core is outlined in this green. And you're going to say, boy, there's a lot of lines. My goal is that any single failure, any single fiber cut takes nobody out of service. So you can go cut any fiber cable. You can go power off any piece of equipment, and nobody knows. Okay? So let me talk, we'll start up at the top here. I do have a REN, and I do have an ISP. We actually do these in repair. Most of the people in my state don't. Only 3 of the big universities do this. We do have an internet exchange point. So I have 2 border routers. Why 2? So that one fails, I'm okay. Each of the border routers is connected to the REN. Each of them are connected to the internet exchange. Each of them connects to the ISP. I move down a layer, and at this layer, I have a core switch. Now, I know I said we don't switch in the core, but when you have enough devices in the core to hook together, you have to use switches. So we have core switches. There I have dual core switches, one in each of my core locations. And I should say, this is a location on one side of my campus, and this is a location on the other side of my campus. Now, the one thing I would do, if I could, and I can't right now, is I would move one of these border routers to this location. And if I could do that, that means that somebody could drive a truck full of bombs up next to one of the cores and explode it, and it'd still be okay. Right now, if I lose this core, I lose my external connectivity. But if I lose that core, all my internal connectivity, I'll show you how that works, still operates. My campus network still runs even if I lose that core. The whole thing goes. I lose external, but I'm still okay to operate inside. So these core switches are attached. They simply attach all of the routers at this level. I have 2 redundant core routers, one in each location. They're mirror images of each other. They have fiber cable, and we still have not yet completed all of the fiber cable for the redundancy, but it's my vision, it's my goal, I'm working on it. Right now, out of this core, I have fiber from this core to every building on campus. This core, I don't yet have fiber to every building on campus. So, I guess I'm lying a little bit, I should remove a couple of these lines. So there's a couple of my buildings where if you cut the fiber cable, they would be partitioned. But my vision is every building is served by 2 fiber cables, 1 to each core. And we continue to work incrementally towards it. And again, each building has a fiber cable to each core. Those fiber cables, I try to keep them in separate conduits, separate pipes, as far apart as possible. Not always possible, but you do the best. Now notice the position of my firewalls here. This is a fairly new development. I used to, when I firewall a section of my campus, I put the firewall down inside of a building to protect the building. The problem that we ran into with that is we were getting too many of them on my campus. Because right now, I don't really know how many buildings I serve. It's maybe 200, something like that. And I just can't deal with that many firewalls. So we are running a thing called the Central Firewall Services. I pull the firewall up where it's attached to the core. And the way this works is this core router, when it is routing packets that are headed towards a building like this, we've played some routing tricks and it sends our traffic to the firewall. The firewall then does whatever filtering, whatever it's going to do, and if the packet is going to be forwarded, then it comes back to the router and is forwarded out. Those firewalls are redundant images of each other. They are connected back to back, so that one of those firewalls crashes, the other firewall has all the state and just picks up and runs. They're connected again. These fibers between the 2 cores are different fiber cables, so if I cut the fiber cable, if I cut this fiber cable, firewall still runs. And same thing with these links here. This is in a different cable than that. This is in a different cable than that. So again, those connections we try to really separate them so any single failure doesn't come out. But that's my campus right there. A simplistic version reality is I have more routers at this level than 2. Primarily, I have 2 that serves the majority of my campus. I do some special things with my residence halls where the students have dorm rooms. I do some special things for my wireless networks that I haven't really shown you. But this is the architecture of my campus. Okay? Any questions about it? Right. Yeah.
There's fiber between the 2 firewalls.
Yes.
Now, what are you doing redundancy for? Is it the fiber? Is it the connectivity? Or the firewall itself?
When you run firewalls in redundant configuration, firewalls build state. They understand the connections that are happening and they understand things. And if the firewalls are going to be mirror images of each other, they have to know what the other person is doing. This is simply a back channel for the firewalls to be copying configuration and state between each other. So that if one of them fails and the other one has to pick up the load, then that other firewall knows what's going on. So for example, an example of something like that is Oracle SQL uses a remote procedure called an RPC mechanism where the remote client will talk to the Oracle server and will say, hey, I need to talk to this database. And the Oracle server will say, okay, yeah, I know who you are, and that's fine. Here's a TCP connection to use, right? The firewall has to know that. The firewall has to track that and understand that, oh, well, I saw this RPC, and then the server told him back, yes, it's okay, and here's the new port number to use. And so if that was flowing through this firewall, right, and that firewall failed, you don't want the SQL session to die because this firewall didn't know that the connection had been moved to some specific port, right? So this is only for configuration and state. There's no connectivity between those, other than the firewalls are copying configuration and state back. Now the firewalls, you can configure them to use the network to do that, but we chose this as an option because I have the fiber available and it's more reliable because there's fewer devices in the path for that state transition. Okay? And this is a technique. Many of the firewall manufacturers allow this kind of scenario, and they use different things, but it's some kind of standby. I'm trying to remember what Juniper calls it. It's standby something, and Cisco calls it something else. But this is a way of using the firewalls such that they are really dual images of each other, and if one of them crashes, nobody even knows. Now, you can do this in an active way or an active-passive way. Active means both of them are forwarding traffic and they're just letting each other know what's going on. You can do it active-passive where only one of them is forwarding traffic and just telling the other what he's doing. Here I'm just doing redundancy with firewalls. Because again, remember my rule in the core. I want any one thing to fail means no interruption to service. None. So if I had a bunch of these buildings that were relying on firewalls and I only had one of them that fails, they're out of service. Right? So again, the reason I have 2, the reason they're connected like this is totally because of the redundancy. Now, everything you see drawn here, I will say, has 2 power supplies. And they're connected to 2 different UPSs. So again, but keep in mind, I installed the first network at the University of Oregon in 1985. My network has had a chance to mature now for 20 updated network plan. This is a very, very established plan. And, I'm still not quite there. I really would like to move one of my border routers to this building. But that's a really big deal, and for a lot of reasons. And I'm still trying to figure out exactly how I'm going to do it. I want to have dual fiber cables to every building on my campus. Still don't quite have it. Right? So I'm still working on this now. It's not there, but this is what I wanted to do. Okay? Right. So just review, route the core, switch to the edge, build star networks, go to daisy chain, buy managed switches. If you guys do this, your campus networks will be okay. Right? You also need to think about where are the bottlenecks in your network. Right. So I'm going to switch gears and we're going to move to cabling unless people want to talk about campus networks. But I'm going to tell you this part, if you follow these simple things, your campus network will be fine. You route the core. Every building has its own subnet. Build star networks. Don't daisy chain. You're going to be fine. Okay?
Suppose you have proportionate numbers of computers taking service from hub. That is, you have only 3 computers taking service from one hub, 5 TVs from another, and 10 TVs from another. Do you have an irregular traffic flow?
On my network, I have very irregular traffic flows, yes. Networks by nature are bursty. Right now, I hope there's not a lot of Facebooking going on, but there's probably some. During the break, there's probably a lot of Facebooking going on. I mean, networks are getting very bursty by nature. The thing that I want, I don't think I can emphasize enough, because right now the biggest problem you guys face is bandwidth and the cost of bandwidth. That's not going to be a problem in 5 years. The cost of bandwidth will be so much less, particularly if you guys get together and do bulk buys and force the pricing. And so all of a sudden, I'm asking you, let's assume that on your campus I gave you a gigabit Ethernet link, gigabit. What problems? Where's your next bottleneck? I removed that bottleneck. Where's your next one? And those are the kind of things you need to be asking yourself, because in 5 years, maybe you won't have gigabit, but you're going to have a lot of bandwidth, a lot more than you do today. And so you need to think about where are those bottlenecks and how can I remove them. Now, again, on my campus, we go back here, and people have asked me how much bandwidth do I have. I'm not quite sure what to tell them, right? So I can draw this. This is 10 gig. This is 10 gig. This is 10 gig. This is 1 gig. Okay? I don't know how you count. I always say I have 12 gig, which maybe isn't fair. But the reality is, bandwidth is not a problem. No user on my campus can hurt my bandwidth. It's impossible. You just can't really do it. So, yes, I do have some bandwidth controls in place, but only on my residential networks, my networks that serve the kids in the dorm rooms, and on my wireless networks, because again, it's the same population as the kids. And the only reason I'm doing that is peer-to-peer is really a big problem in the U.S. campus. Because when you have this unconstrained bandwidth, a lot of the peer-to-peer applications build these things called a supernode. The supernode becomes the server for many, many people. And I don't want my folks to become servers for other universities. So I restrict that bandwidth. And I rate limit all peer-to-peer traffic on my campus to 45 megabits. No more. That's all I'm going to give is 45 megabits. 45 megabits on any one of these links is a little bit teeny blip. I just don't pick up. Just don't pick up. The rest of it, I don't care. People can do whatever they want. But today you go through a lot of work trying to control your users and present about their networks. They're going to show you what their network is, and I'm going to ask them all kinds of questions, and they'll talk about what they're thinking that they need to do, and where their bottlenecks are, and the next kind of things they need to change. Yeah. This is where I simplified my network. I have another router over here, and I have traffic shaping between them. And this router connects like that. So I've simplified this diagram by not showing all my 4 routers. I have another router here that is shaping. But it's only for my residence halls and wireless. That's it. Yeah.
Thank you. Supposing you have two ISP, how do you update the boundaries?
I have 2 ISPs.
Yes.
Okay. You're gonna. Right. So my ISP actually turns out is really me. We run an ISP that provides service to the state. It does have 2 connections. And what you do is you buy enough on each one so that you can fail one and nobody knows. And the way we run it is we of course have an ASN and we have provider independent IPs. We run BGP to the 2 providers. And we use West and Level. Those links are 10 gig. And we line up on one so that even if one fails, the others are plenty to take over the load. And again, this ISP is providing service to every college student in the state of Oregon, every government entity in the state of Oregon, every primary and secondary school child in the state of Oregon. So I'm not going to have any single failure take me out. Right? So I have 2 10 gig connections, and that ISP provides services. But to use BGP, what we do is we don't play any tricks with BGP. We let BGP pick the path, and we let the standard BGP announcements track. And we find we get about 60% of our traffic coming in on this link, about 40% on this link, about 40 on this link. And so 60 on the level 3 link, about 40 on the Quest link is fine. But again, remember, I talked a lot about the exchange points. I talked a lot about the exchange points. We bring 60% of the traffic from my campus goes to the exchange, not even to my ISP. I'm able to bring more of my traffic to the exchange points and to the REN than I do to the ISP. Okay? That makes sense? So if my campus at any minute is using, let's say, 800 megabits, only about 300 are going to the ISP. 500 is going to my peers. And that's, I usually use, anywhere, depending on the day, depending on what's happening, anywhere from 500 provide, some commercial site like Cisco.com, I can't control whether they come in on this link or that link. I can't do it. I mean, I can play around with it and try to push traffic one way or the other, but I can't really control which of those links the traffic comes from. Because I can't control the other side. The other side they might have a 2 megabit link to Quest, and they might have a 10 gigabit link to level 3, and even though I want them to use Quest, they're going to say, no, I'm sending to level 3, whether you like it or not. Right? You can't control it, but other people do. And believe me, if level 3 has a packet that's destined towards your network, no matter, if you're in this situation, if level 3 has a packet destined towards my network, as much as I might want them to be using Quest, level 3 is going to deliver it to me. They're going to get that packet off their network, onto my network as quick as they can. They're not going to send it to some other provider. So this is a real key thing as you look at having multiple connections to multiple ISPs. You can't control what they do. You can't control what people upstream do. You can control what you do. You can control how you're sending traffic out. You can't control how traffic's coming back. Now, any of you who have multiple connections you're using IP address blocks from the individual ISP